Hello guys, so we are going to look at oxidation of carbonyl compound in this lecture. But first of all, we have to understand some basic concepts, and one of those basic concepts is what a reaction mechanism is. Now, I believe each and every one of us have had the idea or know what a reaction mechanism is before now, but let me just define it and then try as much as possible to explain it in the simplest way possible. Reaction mechanism entails the step-by-step process in which reactants are converted to products. For instance, if I have a reaction, let's say this is a reaction A plus B and then coming to C plus D. Now, the step-by-step process in which A reacts with B to form C and D is what is called the reaction mechanism. Now, there are two types of reaction mechanism in organic chemistry. The two types of reaction mechanism in organic chemistry are: one, we have the consacted mechanism, and then two, we have the stepwise mechanism. We have the consacted and then we have the stepwise mechanism. Now, I'm going to expatiate on both of them, like I'm going to actually explain what each of these mechanisms is. Like we earlier said, the reaction mechanism is a step-by-step approach in which reactant, for instance A plus B, is converted to product C and D. Now, the consacted mechanism, as the name implies, consacted means in a single step. It means what? In a single step. Okay? In a single step. Now, let's take it like that. Now, it means those reactions in which reactants are converted to product just in a single step without the formation of any form of intermediate. Are you getting it? For instance, if you want to make your tea, like I've always used this to make examples to illustrate for students. If you want to make your tea, after adding all your ingredients, what do? You just add water to it once and your tea is made by mixing. True or false? There are no specific procedure that you must put your tea first, then put your milk, whatsoever. You can add everything and then mix and your tea is formed in a single step. So those kind of reaction mechanism in which reactants are directly converted to product in a single step is known as the consacted mechanism. Then the stepwise mechanism is a reaction mechanism that involves the formation of reaction intermediates. It involves the formation of reaction intermediate. It involves the formation of reaction intermediate like carbocation and carbanions. Carbanions and carbocations. Now, we said it involves the formation of carbanions and carbocations. Now, what live illustration do we have to actually talk about this? Now, there is something we call akamu here, which is a pap, right? When you are making pap, you need to follow procedures. You don't just make the pap by turning your hot water into it. First of all, if this is the pap, let's say the bowl you want to use to make the pap. Now, discover something, that the first thing you need to do is put in your pap into the bowl, and then the next thing is to bring in water, right? Cold water first. Are you getting it? Now, having brought in cold water, what do? You mix it. You turn the water and the contents of the cup or whatever you want to use. And then when the something must have formed an emulsion, that means it must have formed, let's say, this thick viscous liquid. What do? You now start, but it's not as thick as the final product anyway. Then what do? You add your hot water into it, and then you continue stirring until that thick viscous akamu texture will come out. Now, you discover that while you were making your akamu, you followed a number of steps. You didn't just add the akamu and everything together then mix anyhow. You must follow procedures. in such a way that when you miss any of these procedures, it means that you've actually altered the process of these reactions. Are you getting it now? So that is what the stepwise mechanism is. It takes a number of steps. It doesn't occur in just one step. Are you getting it now? First of all, reaction intermediates are formed. For instance, the carbocations and the carbanions and other reaction intermediate. And then before the reaction may take place. Now we are going to look at some reactions that have this consacted mechanism and some that have this stepwise mechanism, but not in this lecture. In this lecture, we are looking at oxidation of carbonyl compound. What I tend to do here is just to water down the ground in order for us to actually understand the concept that we are talking about today. Not that we are writing reaction mechanism. Some persons be like, why is this one coming here? Why is this one not doing that? Okay. Now, having discussed the reaction mechanism and then the types of reaction mechanism, now let us define the reagents that are used in reactions. Now we have what is called a nucleophile, okay, and then we have what is called an electrophile. Now the question is, what is a nucleophile? I believe every one of us as chemistry students must have heard of this before we come to learning of oxidation of carbonyl compound, right? Now a nucleophile is an electron-rich species. Is electron-rich, and in most cases, because it's electron-rich, the nucleophile is generous enough to always give out electrons. Are we getting it? To an electrophile, which is an electron-deficient species. So we can say that the nucleophile is an electron-rich species. It is always the attacking reagent in almost all organic reactions. It's the attacking reagent because it's bringing in its own electron. Are you getting it now? So that is that. Nucleophiles are electron-rich species and they are the attacking reagent in most organic reactions. Then we have the electrophiles. Electrophiles are electron deficient. Electron deficient, and because they are electron deficient, we can say they are electron loving. You tend to love what you don't have. They don't have electrons. We say they are electron deficient, and then they do what? They actually accept electrons. Okay, now in most cases the electrophiles are at the receiving end. Are you getting it? They receive electrons from the nucleophile. They receive electrons from the nucleophile. We can say they are electron receiver. Now, nucleophiles are Lewis bases. We know what Lewis bases are. Electron-rich species. Lewis base, I'm writing an acid here. And then electrophiles are Lewis acid. Okay. Now, have a look at the nucleophiles, the electrophiles, types of reaction mechanism. Now, the question is, how are reaction mechanism written? How do we write reaction mechanism? Because we cannot begin to illustrate in organic chemistry. We cannot begin to write everything. For instance, add your base, add your acid, add your reagent, and then mix together. How do we actually carry out this reaction mechanism in organic chemistry? Now we use arrows to illustrate how the electrons or how the reaction takes place. This is the most important concept that you need to understand. We use arrows to illustrate how the reaction actually takes place. Now, if you are moving, for instance, let's say this is a reactant. Now, if this reactant has 2 electrons, or if it has 2 electrons, and you want to move these 2 electrons to, let's say, this that does not have. Now, what you normally do is to use a full arrow to show the direction of electron movement. You use a full arrow to show the direction of electron movement. Now, discover that the arrow is pointing from the nucleophile, which is the one that is electron rich, to the what? Electrophiles, which is the one that is what? Electron deficient. Okay? Hope you understand that concept. In every organic reaction, you use arrows to actually indicate the movement of electrons. The arrows will tell you how the reaction is proceeding, because most reaction involves either the movement of electrons, proton abstractions, etc. Are you getting it now? So, in this case, what we ought to, or what we are looking at, is how these electrons are moving from the nucleophiles to the what? Electrophiles. And look at something. You discover that the electrons or the arrow usually has its base on top of the nucleophile, and then it's coming to the word electrophile. So when you're writing reaction mechanism, the arrow usually points in the direction of the word electrophile from the nucleophile. Now this is for an electron or an atom or a reactant that has lone pairs of electrons. Now these lone pairs of electrons can also be in the form of, let's say, something, a negative sign here and then B here. What do? This one also moves here. It tells you that this electron is leaving here to come and what? Attack here, or this. So you now understand how this reaction actually take place. Now, how about a situation where you are moving just one electrons? Now, there are some reactions that involves the movement of only one electron. For instance, if you have one electron like this, now those of us that learned organic chemistry last semester, you agree with me that we said that whenever we have just one electron like this attached to an atom, we say this is a radical. Okay, so we say this is a radical. Now, how about you want to show how radicals are moved? Let's say you want to actually use this radical to attack this B here. Now, how do you do that? Would you use a full arrow? No. In this case, you are not going to use a full arrow, but you are going to use a half arrow. Are you getting it? To indicate how the electron move. Now, note the difference between this and it. You discover that this one is something like this with two full head arrow. Are you getting it? Same thing is applicable here. This one is also from here to here like this, full arrow. But when you want to show how one electron is moved, you use what? Half arrow. So I believe I've watered down the ground for you to understand what reaction mechanism is, how to write organic reactions, etc. Are you getting it now? Now, bonds can also be moved. For instance, if I have A bonded to B and then this is C here, I want to move this bond from A to B to C. I want to move the bond between A and B to C. Let me write it with the right. Black is for writing, and so let's say A and B, they have electron, and I want to move this to C. Now recall that this two here, this bond here means two electrons. For what we know before now, that two electrons make a bond. Okay, so if I want to move this from here, what do? I do this, and then this moves to this point here. Is that understood? This one moves with it to this point. Why this one will be positively charged, this will be negatively charged. I mean, why this will be this will be negatively charged here. So that is how to write the reaction mechanism. We said it's a step-by-step process in which reactants are converted to products. We have two types, the stepwise mechanism and then the concerted mechanism. Now, we have nucleophiles and then we have electrophiles, okay? Now, what I actually intend to do here was to talk about the Aldol condensation reaction. Now, what is the Aldol condensation reaction? Now, Aldol condensation reaction is a reaction whereby an aldehyde and a ketone containing alpha hydrogen undergoes self-addition in the presence of a base to form a product called aldol. The reaction is called Aldol condensation reaction. Now, first of all, what is the aldehyde functional group? As your three students, we ought to know what the aldehyde functional group is and what the ketone functional group is. Now, the aldehyde functional group is R, C, double bond O, and then H. This aldehyde, and then this R, double bond O, and then R. This is what? Ketone. Where R is an alkyl group, okay? Now we have the alkyl group, which could be anything. Now, for instance, if I have an equation given to us like this, let's say, a compound given to us like this, that you agree with me that this is an aldehyde. However, if I have CH3, C double bond O, CH3, this is a ketone. Are you getting it now? Now, what is the alpha hydrogen we are talking about? What is the alpha hydrogen we are talking about? Now, the alpha hydrogen is the hydrogen that is on the alpha carbon. Now the question you will now want to ask me is, which of the carbon is an alpha carbon? Now whenever you look at any compound, first of all, this is the functional group, right? Now any carbon very close to that functional group is an alpha carbon. So in this case, this carbon here is alpha carbon. This one here is an alpha carbon, okay? Also here, this is what? An alpha carbon, because this is the functional group, the carbonyl functional group, okay? So this carbon here is the alpha carbon. Now when you come here, this is the presiding functional group here, because carbonyl functional group has a higher priority as compared to the alcohol functional group here. So in this case, this is the functional group, and then we can now say this is the alpha, this is what? Beta, and then this is what? Gamma, and it continues like that. So if I give you a compound and I ask you to determine the alpha carbon and the beta carbon, I believe you should be able to determine that. For instance, if I say CO, and then here is H, and then we have CH2, 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 and then CH3. And here is, let's say, here is the presiding functional group, right? Everyone knows that. Now, if here is the presiding functional group, it means here will be what? Alpha, here is beta, here is gamma, and then it continues like that. Okay? So, whenever the compound or the aldehyde or the ketone has this alpha hydrogen, it can undergo a self-addition reaction. It can undergo what we call a condensation reaction. Now, what is a condensation reaction? Let me use something to illustrate what a condensation reaction is. Condensation reaction is a reaction whereby a small molecule attacks another small molecule to form a very large molecule with the elimination of a very small molecule. Notice the difference. I said a small molecule. For instance, this react with this. These are two small molecules. Are you getting it now? To form a very large molecule with the elimination of another small molecule. Now, in this reaction, water molecule is given off. Okay? Water molecule is given off. So that is what the Aldol condensation reaction is all about. But in this Aldol condensation reaction is either an aldehyde or a ketone must have an alpha hydrogen, undergo self-addition in the presence of a base to form an aldol. Now, the name aldol is so called because it contains the aldehyde, the product. The product contains an aldehyde and what? Now, the question is, these two reactants, what are they? Now, you agree with me that this is an aldehyde. The screen is already too. Let me erase some highlights. Now the question is, what functional group is this? You agree with me that this is an aldehyde, okay? It's called entanal. Now, in the same vein, what functional group is this? This is also entanal, which is also an aldehyde. Now, the product that is formed is called a beta hydroxy aldehyde or beta hydroxyl aldehyde or a beta hydroxy ketone. Okay? Beta hydroxy aldehyde. That is if the product or the reactant that reacted are all aldehyde molecules. It forms a beta hydroxy aldehyde. Now, why do we call this a beta hydroxy aldehyde? Of course, we know the presiding functional group here is an aldehyde. Is that not so? So if you look at this, this is alpha. This is the presiding functional group. We say here is what? Alpha. Here is what? Beta. It means that at the beta carbon, there is OH group. Are you getting this now? So we call it a beta hydroxy aldehyde. So we can now say that the Aldol condensation reaction, let's take it this way, is a reaction whereby an aldehyde or a ketone containing alpha hydrogen undergoes self-addition. Now listen, it undergoes what kind of addition is this? It's called nucleophilic addition. Okay? is called a nucleophilic addition reaction, not just electrophilic or any kind of addition reaction. It undergoes self-addition reaction in the presence of a base to form a product that is called an aldol. This product is what is called the aldol. Now you know why it is called the aldol now, because I told you that it contains the aldehyde and the alcohol functional group. You can see this as alcohol, then this is the aldehyde functional group. Now, another thing that you must know is that in Aldol condensation reaction, the two reactants that form the product must be the same, because we said it undergoes self-addition reaction. So in this case, you saw that this is entana, this is what entana. Both of them react to form a beta hydroxy ketone, aldehyde. Are you getting it now? So if what aldehyde is this one? Can you now say this is beta hydroxy 1, 2, 3, 4 butyrate or butadiene, beta hydroxy butadiene? Are you getting it now? So that is for the Aldol condensation reaction. Now, the reaction takes place in the presence of a base. Another thing that you need to know is in Aldol condensation reaction, like I told you earlier, the product is usually a beta hydroxy aldehyde. Now, how about if it were to be ketone that reacted together? The product will be beta hydroxy ketone. And that compound or the aldehyde on the ketone that react must have alpha hydrogen. So there are some compounds that do not have alpha hydrogen. For instance, if you look at this compound, this formaldehyde. Look at formaldehyde very well. Do you see any alpha hydrogen here? So this compound like this cannot undergo the Aldol condensation reaction. Why? Because there is no alpha hydrogen. This is a functional group. Before it can have alpha hydrogen, it means that there is another carbon to which this hydrogen is attached to. There is no alpha carbon here. So there is no alpha hydrogen. Is that understood? So let us look at the mechanism. Now, mechanism is like how this reaction is formed. Now, paying attention to everything that we did initially here, you should be able to write the reaction mechanism for this reaction. Now, the first step, we said the enolate ion is formed. Now, for instance, let's look at this reaction. This is entana. Let's use entana. Entana is CH3, C double bond O, and then H. And then we are told that the first step of the reaction is that the enolate ion is formed. Now, which of them is the enolate ion? Now, what we are doing is we want to show you how this reactant, which is aldehyde and this react to form this. Are you getting it? How is this reaction possible? That's what I'm trying to show to you. So I picked one of the reactants first, which is this. Recall that there are two of them. They must be the same. That's why you call it self-addition reaction. Self means with yourself. Are you getting it now? So coming back here, we have the aldehyde. Now, how do we convert this to the enolate ion? Is first of all by reacting it with a base. The base can be sodium hydroxide. It can be any of these bases. Are you getting it now? But in this case, let's use sodium hydroxide. Now, the sodium hydroxide that reacts is not the full sodium hydroxide that will react here, but rather the nucleophile in this sodium hydroxide, rather. Now, the nucleophile here is, if sodium hydroxide splits, it will form what? Sodium plus and what? OH minus. The OH minus now is a perfect nucleophile. So we can now say that the OH minus will react with what? The OH minus will react with what exactly? It's going to react with the alpha hydrogen. So here's the alpha hydrogen here. Now you agree with me that this is the functional group here. So everyone will also note that this group here, carbon here, has 3 alpha hydrogens. Okay, so I can say that this alpha hydrogen, the 3 of them, let me bring one out that will react with the base. So I will have something like this: CH2 bonded to one hydrogen. You know, when this hydrogen bond with this CH2, it forms CH3. The reason why I have to bring it out like that is so that the hydrogen can easily react. Okay, then we have C double bond O, and then we have what? H. Now, what is coming in to react is the what? Is the base, which is what? OH minus. Now, according to what I taught you, what did I teach you? I told you initially that whenever this reaction occurs, what happens? The nucleophile is usually the one that goes to abstract a proton. Look at it. So if I want to draw my arrow now, I will start from the nucleophile and then straight to the what? Electrophile to abstract a proton. So there's proton abstraction. What I mean by proton abstraction, it means a proton is being taken away from the enolate. From the aldehyde to form the enolate ion. Now, as this proton is coming here, look at what I'm doing. This minus is coming here, is a nucleophile. It collects this hydrogen. Now, it's taking a proton. What is a proton? A proton is positive what? Hydrogen. As it's coming to take the proton, what do you observe? The proton is not carrying this electron along. There's a bond here, right? Between this carbon and this hydrogen. True or false? The proton is not taking this bond along. Why? Because a proton is a positive what? Charge. We are not talking about the electron. You know, hydrogen has both the electron and then the what? Proton. What it is taking, what this negative here is taking is the proton and not the what? Electron. So the electron will still be there. It means that automatically this bond here will still remain. Now this bond cannot stay here. So what will happen? The bond will come to this carbon here and come and form a negative charge on that carbon here. So you see how these electrons are moving. First of all, the OH attacks the proton and abstracts it. That means it removes the proton. And then this bond here, because the proton is not taking this electron here, this bond here is taken into this carbon here. So what do you think will be the product of this step? The product will be CH2, and then we have what? Negative, and then we have C, double bond O, and then we have H. This product here is what is called the enolate. Is that understood? This product here is what is called the what? Enolate ion. Now, the next step is that the enolate ion attacks the carbonyl carbon of another unionized aldehyde molecule. Recall that we said there are two aldehyde molecules. One has been ionized to give the enolate ion, which is this. Now, if we took this first, it means we are now coming to what? Or let's say this one was the one we took first, because this one was the one that have that hydrogen up, right? This is the one that have hydrogen either up or down, whichever position you want to place it. So this one is the one that is what? Unionized. Now let's take this one out and react it with the one that is ionized. So what we are going to have here is something like this. Let's bring out the unionized, which is CH3, C double bond O, and what? H. So in this reaction, you discover that we are using two aldehyde to N plus the CH2, and then we have C double bond O, and then H. This is negative here. Now let's note something. This is unionized, okay? And then this is what? Enolate ion. Of course, the enolate ion is ionized. Now, which of them do you think has a nucleophile here? Now, you agree with me that this negative charge here under is a potential nucleophile. And this nucleophile can easily attack this positive charge here. This is a carbon here. Do you know why? Because this carbon atom, this oxygen here, it makes this to be partially positive. Are you getting it? It makes this carbon to be partially positive because oxygen is more electronegative than what? Carbon. So it makes this carbon here to be partially positive, and then this oxygen here to be partially what? Negative. So it means that this one is positive and this is what? Negative. And positive and negative what? Can actually attract or can react. Now let me come back again. The carbonyl group is something like this. Oxygen is more electronegative than what? Carbon. So it means that the oxygen will be drawing the electron cloud to itself, making it to be partially negative, and this as partially positive. These are some of the things that we did in first semester organic chemistry, okay? So when this negative charge here attacks this position, according to mesomeric effect, when an attacking reagent is coming here, the valency of carbon will be more than the required valency. Or if I want to make things easier, I can decide to say, let this hydrogen not be here. Let me put the hydrogen under here so that to make the something looks more presentable. Because the hydrogen under here is still the same thing. Abi? We had the hydrogen here before. I said, no, it shouldn't be here. Let me put it under here so that it will make this something to be very easy to react. Okay? So this, now, we attack this position. As it's attacking this position, according to mesomeric effect, Those are the things that we learned first semester, and those factors that influences organic reaction. According to mesomeric effect, it says that carbon must have a valency of how many? 4. So whenever an attacking reagent is coming here, what do you say? It means that this double bond we have to break and then pack on top of this oxygen here. And I told you that each of these steps are actually indicated with arrow. So this one of the electron here, the 2 electrons here, 2 electrons make a bond, right? So this bond, we believe, are come and pack on top of this oxygen here to form a negative charge. So the product of this reaction now will become CH3. Then we'll have C. What do we have here? Hydrogen. And then what do we have here? O negative, right? Now this negative here will form a bond between this carbon and then this carbon. Okay, form a bond between this carbon and this carbon. This negative charge here will form a bond between this and this. So this will form CH2 and then CHO and then H. You now see the product that is formed. So we can now say that a bond is formed between the carbon of the carbonyl carbon. This is the carbonyl. When you say carbonyl, it means the carbon that is carrying the what? The C double bond O. So where is the bond formed? We can say the bond is formed between the carbonyl carbon of the unionized. Are you getting it now? Of the what? Unionized. It's formed between the carbonyl carbon of the unionized and the alpha carbon of the what? Enolate ion. And the alpha carbon of the enolate ion. So let's take note of that. That the bond is formed between the carbonyl carbon of the unionized and the alpha carbon of the what? Enolate ion. Because here, this is like the alpha carbon. Okay? This carbon here. We say this is the functional group. Then the carbon close to it should be the what? Alpha carbon. So this is the product that will be formed here. But this is not the product of Aldol condensation reaction. Okay? So the next step is the negative ion in the product accepts a proton from water to give the Aldol. Now the product we have is something like this: CH3, CO minus, this H, and then we have CH2, C double bond O, and then H. I believe this is the product that we have. Okay, this is the product. Now, what happens here is that water molecule will give a proton to this. Now, water molecule is what? H2O. True or false? Water molecule is H2O. Now, if you want to write the Lewis structure, we say this is oxygen, this hydrogen, and then it has two lone pair of electrons, which is 1, 2, 3, 4. So water molecule can come and react here. Now, how does that reaction take place? Let me draw this down so that it will make more sense. Let me draw this down. Now we have CH3, then we have CO negative, CH2, C double bond O, and then H. Are you getting it now? Then we have water molecule, which is hydrogen, and then oxygen, hydrogen. Then we have the two lone pair of what? Electron. This is water molecule, right? Now, what happens in water molecule? A proton will be abstracted. Water molecule can, because water is part of the reaction already, so it can donate electrons. I mean, it can donate its proton. Are we getting it now? So, how does the proton abstraction take place? You know, this is negatively charged, so this is a nucleophile. So, what happens is that this one will come, take a proton from water, and then this will come, pack on top of this. Are you getting it? Because I told you that whenever a proton is being taken, it means that the electron still remains. So this bond here still remains. Okay? So this bond here will pack on top of this. So what do you think this will now form? Normally this is OH. So this will be OH. Because this bond packs on top of here, that bond will now form a negative charge here. So we are left with what? OH minus. Why this proton is being taken by this negative charge here? You know proton is what? H plus. So when H plus attack OH, when H plus attack O minus, what will it form? OH. And that is why we have the product as what? OH. So this product will become CH3, Here is what? OH, and then here is Ca. This hydrogen under here, sorry about that. This hydrogen under here, CH2, C double bond O, and what? H. This is what is called the aldol. Are you getting it now? This is what is called the aldol, because it contains the aldehyde and then the alcohol functional group. Now, what do you think is the name of this aldol? What do you think is the name of this aldol? We can say that this is beta hydroxy. Now we can say that this is beta hydroxy 1, 2, 3, 4 butadiene. Okay, beta hydroxy butadiene or butana. You can say this beta hydroxy butana, or you can say this 1, 2, 3 hydroxy butana. So that is the product of this reaction. Okay, that is all for the Aldol condensation reaction. Now let us look at some of the properties of Aldol condensation reaction. Now the properties are: the product in Aldol condensation reaction have several common characteristics. The common characteristics is the product is a larger molecule that contains a newly formed carbon to carbon bond. I've explained this before, that at the end of the Aldol condensation reaction, what is actually formed is larger than the initial reactant that reacted, and it usually involves the formation of another carbon-carbon bond. Are you getting it? Between what? Can we still remember what I said? I said the new bond is formed between the carbonyl carbon of the unionized aldehyde and the alpha carbon of the enolate ion. Okay, so that is that. Now let's look at the next point here. Say the newly formed carbon to carbon bond occurs between the alpha carbon of one aldehyde molecule and what was originally the carbonyl carbon of the second aldehyde. I've explained this before. Okay, so I've explained this too. The product contains two functional groups, one carbonyl and one hydroxy group. Everybody knows that. The product contains two functional groups, one the carbonyl and the other one is what? The aldehyde. And then the other one is the hydroxy group is always attached to the beta carbon, which is 2 carbon away from the carbonyl carbon. Look at it here. This is the beta carbon. So here's the hydroxy group attached to the beta carbon. Now that is why we call it the beta hydroxy butadiene or beta hydroxy butana. Or we can generalize it by saying that it is the beta hydroxy aldehyde. Now the next one is that. So now there is retro-aldol addition. Retro-aldol addition means if you add the base, let's say sodium hydroxide. If you add the base, let's say sodium hydroxide, and then water to the beta hydroxy, this is the beta hydroxy aldehyde that was initially formed. You would be able to obtain the reactant or what reacted. Are you getting it now? It means retro means before. That means before what is formed or was formed. What were the initial reactants that reacted? For instance, I have A plus B is equals to C. Now, if I break C down, what are the things that I'm going to see? Am I going to see A and B? That's what is called the retro-aldol addition. Now, for instance, let's say we cooked a pot of soup, and then when you cook the pot of soup, you put meat, and then you put fish, right? And then you put periwinkle, let's say periwinkle, and some other ingredients. Let's say you put vegetable, okay? Vegetable. Now, this is your product that is formed. Now, what about if we decided to, let's say, wash this soup off and wash the ingredient, the things that we are inside this, wash everything off. Now, you agree with me that you will still see the periwinkle inside because it's non-decomposable. Are you getting it now? In the same reaction, you are going to see the meat, Let's say the soup got spoiled, sad. You're going to see the meat, you're going to see the periwinkle, you're going to see the fish you used in cooking it. True or false? It's true. That's why we are trying to talk about retro-aldol reaction, like playing back. Now, this is our aldehyde, beta hydroxyaldehyde. How about if we add sodium hydroxide plus H2O? Are we able to get back the initial things that reacted? For instance, look at the one we solved here. This one in such a way that two aldehyde molecules give us a beta hydroxy. If I should break this down by adding water and sodium hydroxide again back into the reaction, will I be able to get the aldehyde, which is the N-tannal and the N-tannal that reacted? That is what is called the retro-aldol. Retro means play back to retro-aldol reaction. Now, let's take, for instance, this one. Let's see if we'll be able to know the reactants that reacted to form this. We have 2-ethyl, 3-hydroxyhexanal. Which reactant do you think actually reacted to form this? 2-ethyl, 3-hydroxyhexanal. Now, let us draw the structure of this compound. 2-ethyl, 3-hydroxyhexanal. Now, this is the structure of 2-ethyl, 3-hydroxyhexanal. Okay, this is the structure of 2-ethyl, 3-hydroxyhexanal. Now, this is the first carbon 1. So here is what 2. We have the ethyl group here. Okay, 2-ethyl, 3-hydroxy. This is 3. This is 4, 5, 6. 6 making it hexanal. 3-hydroxy means at position number 3 there's hydroxy group here. Is that not so? Now the question is, which reactant do you think actually formed this product? Now in aldol reaction, it's very easy to determine because the two reactants must be the same. True or false? The two must be the same in aldol condensation reaction. So what you just need to do is, at where the OH end here, divide it here. Are you getting it? And then here is 1, 2, 3, 4. Is understood? You count it backward. Now, this fourth one tells you that the aldehyde that reacted is a 4-carbon aldehyde. So you come here and say, what 4-carbon aldehyde will have is butadiene or butanal. So the two products that reacted to form this compound is 2 butanal molecules. Are you getting it now? Not 2 butanal like 2 butanal, is butanal molecules that undergoes the Aldol condensation reaction. Are you getting it? That is the product of that reaction, and that is why we say that in this case, what we are taking note of is just divide it into 2 here. From here down should give you one part of the molecule that reacted. Are you getting it? Then from here down should give you the other part. Look at it. This is 1, 2, 3, 4. Abi? Now from here is how many? 1, 2, 3, 4. 4 react. 4 aldehyde is what? Butanal. Is that understood? The reason why they have to bend this one down is you must use the what? The alpha hydrogen to react. That was why they have to bring this one down so that the alpha hydrogen can react with the what? With the unionized molecule. Are you getting it? The alpha hydrogen have to form the enolate, and for it to react, you have to bring every other thing down, because if you continue this chain, it means that this thing will give it issue. That is why we have to bring this one down. Is that understood? And that was why the ethyl came about. Do you understand what I'm trying to say? I guess you understand. What I mean is, recall that aldol condensation reaction is usually between the what? Alpha hydrogen. The enolate ion is formed by the alpha hydrogen. So if this were to be butanal molecule initially, which is H, and then here is what? CH2, CH2, CH2. Now this is what? 1. This is what? The carbonyl. Then this is the what? The alpha. Now, if we use this alpha to react, it means that every other thing that is attached to this alpha carbon have to form a substituent under, because according to steric hindrance in chemistry, if this CH2 is here, it will actually hinder the reaction. So this one has to come down as a substituent, and that's why we erase this part to now form a substituent under, which is CH2, CH2. Then when this one now react with the other aldehyde is something like this: CH3, CH2, CH2, C double bond H. This is butadiene now. So when this one attacks here now, this one goes up. It's now formed the product in such a way that when these two bonds now form, or when this now form a bond between this, automatically in chemistry, this becomes a substituent. Is understood? So what you are going to do for me now is, as a practice question, is look at these molecules very well. 4-hydroxy, 4-methyl, 2-pentanone. This is pentanone. It means that what actually reacted is what? Ketone. And 5-ethyl, 5-hydroxy, 4-methyl, heptanone. Are you getting it? Look at these two structures and then tell me the reactions, or what the two reactants that reacted to form that product. Okay? Now, what I'm going to do is, I think I should actually use another example to illustrate Aldol condensation reaction without. Let me use another molecule entirely. Okay, let me clear our screen, erase our ink. Now let's use, in this case, let's use propanol. Propanol is what? CH3, CH2, and then C double bond O H. Abina, this is structure of propanol. Now the question is, to form the enolate ion, I told you that a base react. Is that not so? A base react. Now the base is what? OH minus. But before the base must react, it means we must bring our alpha hydrogen out. Is that not so? And for the alpha hydrogen to come out, this is what? The carbonyl group, and this is the what? Alpha carbon. It means that the alpha hydrogen is found here. I told you that what will happen, this CH2 will now come on that, so that the alpha hydrogen can easily react. So this will form C double bond O. Here is what? H. Here is what? CH2. And here is what? Here is CH3. Okay? Now, what we are going to do, CH2, CH3, is remove one hydrogen from here and bring it up here, so that this alpha hydrogen now can now react with what? With OH negative. We say the OH negative is what abstracts the proton. Okay? So when this OH negative abstracts this proton, this bond here will come here to form a negative charge. I go slap. Now, at the end of the day, what do you think will be the product here? The product will now be CH. We'll have the negative charge here, and then we'll have C double bond O, and then H, and then CH3. Now, of course, when this reacts with this, what we are here expecting to form, you know, this proton that is coming is H plus, leaving here to this. So we have H plus plus OH negative. What we are here expecting to form, we have to form what? H2O. This H2O will later work at the other part of the reaction. Okay? Everyone knows how. Now, when this is the enolate now, right? Now, this enolate ion will attack an unionized propanol. This propanol. So the enolate ion will attack it. So we have CH3, CH2, C double bond O, H. This is unionized. And then this is what? CH negative. Here is what? CH3. Here is C double bond O, and here is what? H. Okay? Now, at the end of the day, what do you think we are going to get? If this one attacks here, this one will come up. True or false? That is the process we said we ought to follow. Now, I told you that this, we may make it in such a way that this hydrogen should be under here. It's still the same thing. So when this one attacks here, what happens? This one goes up to form a negative charge. So we are going to form something like this. CH3, CH2, CO minus. Here is hydrogen. Here is CH. Here is CH3, C double bond O, and hydrogen. Okay? That will be the product there. Now, finally, what is the next step for us to take now? Next step is hydration. That means the product will abstract a proton from water. Are you getting it? To form the final product. So let me erase all. Okay. So what do we have here? CH3, CH2, CO minus, this H, here is C, and then here is CH2, or here is CH, CH3, C double bond O, H. I believe this was the product that was formed. Okay, yeah. Now we said water will donate a proton. Is that not so? Now what is the structure for water? We said it's HOH, which is H2O, right? So this water will abstract a proton. I mean, the proton will be abstracted from water, right, to form, because a proton is what? H plus. I've explained this before. O minus and H plus react. What will it form? OH. Then this negative charge here will now come on top of water to form OH negative. So finally, the product of this reaction will be CH3, CH2, C, here will be what? OH, here will be hydrogen, here will be CH2, sorry, here will be CH3, here is C double bond O, and here is H. And what is the name of this product? This product now is 1, 2, so you call this as 2-methyl 3, 1, 2, 3, 3-hydroxy. Then this 1, 2, 3, 4, 5 pentanal. 3-hydroxy pentanal. So that is the product of that reaction. Now, the last step, the last thing that we need to know here is that this product of Aldol condensation reaction that is formed, it can easily be dehydrated either by heating or treatment with dilute acid to form an alpha beta unsaturated aldehyde. The product can easily be dehydrated by heating or by treatment with dilute acid to form alpha beta unsaturated aldehyde. Now, this kind of reaction is what we call elimination reaction. Now, we know what elimination reaction is, right? We say elimination reaction is a reaction by which the two molecules or two atoms are removed. For instance, OH and H are removed from a saturated compound to form an unsaturated system. Okay? So, in this case, look at what they did. This hydrogen here, right? And this OH here is removed. And when it is removed, what do you think will be formed here? A double bond. Okay? So that is the product that is here, which is CH3, C, double bond and C, and then C double bond what? O and H plus H2O. Is that understood? So this is the type of elimination reaction to form an unsaturated. Now this is what? The product of Aldol condensation reaction, which is a beta hydroxy aldehyde. Okay, this is a beta hydroxy aldehyde. Beta hydroxy aldehyde. Okay, now in chemistry, whenever you see this symbol here, it means heat. You can either heat or treat it with dilute acid to form alpha beta. Now, what carbon is this? Carbonyl. This carbon here is what? Alpha. This is what? Beta. So the elimination usually occurs between the alpha carbon and then with the beta carbon. So when the elimination occurs between the alpha and beta, it's such a way that hydrogen is removed from here and this OH is removed from here. What is formed is what? A double bond, which is an unsaturated. Most times it's usually called an alpha beta unsaturated aldehyde. Okay, now the next one is this. For instance, if you look at this one, where do you think the bond will be formed? First of all, this is a carbonyl compound. Don't mind this structure the way it is written like this. This structure is still the same thing with this structure here. Are you getting it? All in a bid to confuse you. Don't be confused. Don't be bamboozled. Don't be bemused. Don't be bamboozled. Now, what you do here is very easy. This structure is still the same with this structure. Let me bring it out and show to you that it's the same. What do we have here? CH3. Abi. Now, what do we have here? CH. Abi. Then the next one is what? OH on top. Abi, there you have C. This place here is a carbon, and of course, you know, for the valency to be complete, it has 2 hydrogen. Okay, which one can be on top here, hydrogen, and then the other one here, right? Then we have this carbon here, carbon, double bond O. Okay, and then finally, what do we have here? Hydrogen. So you see that this structure here is still the same thing with what you have here, but just in a bit to confuse you, do it like this so that everybody will be, ooh, chemistry is hard. It's not hard. It's the same structure. Okay. Now, at the end of the day, the product that is formed is still the same thing. So we say this is a carbon here. Hence, there's one hydrogen here and then another hydrogen here. This is a carbonyl carbon, right? Now, the carbonyl carbon, it has, after the carbonyl, we have the alpha and then the beta. So it means the OH should be removed from here, and then the hydrogen removed from here, and then the double bond will be formed here. That is why this double bond is formed here. Okay? And this is the product of this reaction. Now, this product, these two things are still the same. CH3, CH3, CH, CH, double bond, CH. This place here, there is a carbon, hydrogen. Then we have CO, which is CO, and then we have a hydrogen, plus what? H2O. Where the H2O come from? OH plus H is what? H2O. And that is the product of that reaction. That is why this is the product of that reaction. So whenever the aldehyde, they can be dehydrated to form what? Alpha beta unsaturated aldehyde. It must be alpha beta unsaturated aldehyde. So we've been able to look at the Aldol condensation reaction, everything about the Aldol condensation reaction. We said the first step to getting your product is that the enolate ion is formed. Step 2, the enolate attacks the carbonyl carbon of another unionized aldehyde molecule. Are you getting it? Paying attention to all those resonant mesomeric effects and the rest. And then lastly, the negative ion in the product accepts a proton to form water to give the aldol. We said the reason why it is called the aldol because it contains the aldehyde and then the hydroxy functional group, which is the alcohol. From the name aldehyde and alcohol. Remove OL here and then remove ALD. So it becomes ALD plus OL, which is the aldol. That is why that product is called Aldol condensation. We talked about the several structural characteristics of all Aldol condensation reaction, which we discussed in details. And then we have all these 2-ethyl 3-hydroxy hexanal. Okay? And then what you are going to do for me now is, this is for ketone. We didn't do any practice question for ketone, but it also follows the same approach. Okay, should we try one for ketone? I'm going to do it to half this thing if time is not, because I'm supposed to end the video in 1 hour. So for ketone, for instance, ketone, let's say you have CH3, C double bond O, CH3. Any one of them can react because this is what? Alpha hydrogen here. This is alpha hydrogen. So ketone has how many alpha hydrogen? 2 alpha hydrogen, right? So let's use this one. So this becomes CH3, C double bond O, CH2, then 1 hydrogen up here. Now what did we say? We say OH minus will come to abstract a proton, okay? According to the process we'll be doing. So when you abstract this proton from here, this one will kick in to form a negative charge. Okay, so this will give us CH3, C double bond O, and then CH2 negative. Are you getting it? Plus H2O. Now this one now is the enolate. We said this enolate ion will react with another ketone molecule. So you have CH3, C double bond O. Let's put this CH3 here. Are you getting it? Bring it down so that it can easily react. Plus the enolate ion, which is CH3, C double bond O, and then let me turn it. You can turn it upside. You can turn it this way, right? So here becomes CH2 negative, C double bond O, and then CH3. Now, what do you think is happening here? There will be attack by this nucleophile to this position, and when that happens, this one come up, right? So the product will become it's still the same process. I'm just trying to show you how we can use it for ketone too. CH3, here is minus, here is CH3, and then here is CH2, C double bond O, and then here is what? CH3. Okay, now what do you think will happen here? There will be hydration, right, which is the final step. I mean, not hydration, it will take water, I mean hydrogen from water, right? So if you take hydrogen from water, let me just do it here. Chapali is already 1, so 1 hour. My video shouldn't be more than 1 hour. So when this one attack here, what will happen? H will be here, hydrogen will be here, and then this is the product of that reaction. Thank you very much for your time. Okay, bye bye. We'll see in our next lecture. Now, we've talked about the Aldol condensation reaction. Now let us look at the mixed Aldol condensation reaction. Now, as name implies, mixed means maybe two different carbonyl, one of which must have an alpha hydrogen in the presence of a base, is known as the mixed Aldol condensation reaction, a reaction between two different carbonyl. Now, you recall that the ones that we did initially were between the same carbonyl. For instance, between two acetaldehyde molecule, or between two propanol molecule, or between two propanone molecule, which is ketones. Are you getting it now? So in a situation where the reaction between two different carbonyl, one must be an alpha hydrogen in the presence of a base, is known as the mixed Aldol condensation reaction. For instance, acetaldehyde reacts with benzaldehyde in the presence of a base to form cinnamaldehyde. Now, what is acetaldehyde? We've looked at the structure of acetaldehyde, which is CH3, C double bond O, and then you have what? H. Now, what is the structure of benzaldehyde? Now, benzaldehyde has this structure plus the benzene this is structure of benzaldehyde. Now, the question now is, which between the acetaldehyde and benzaldehyde has this acetaldehyde? I'm supposed to use a red pen to indicate this. Acetaldehyde and this is benzaldehyde. Now the question is, between acetaldehyde and benzaldehyde, which of them have an alpha hydrogen? Now you agree with me that benzaldehyde does not have an alpha hydrogen. Why? Because this is the carbonyl group here, right? Now this is supposed to be the alpha carbon, but this carbon, it has 1, 2, 3, 4 bonds. So hence this one does not have an alpha hydrogen. Are you getting? So we can indicate here no alpha hydrogen. However, acetaldehyde have what? Alpha hydrogen. This is the alpha hydrogen here. That's why we said that a reaction whereby two different carbonyl group in such a way that one of them have an alpha hydrogen is what is called the what? The mixed Aldol condensation. Is that understood? The mixed Aldol condensation. Two different carbonyl group. Are you getting it now? So now, if I react this with this, what do you think I'm going to form? Now, first of all, I'm not going to write the full reaction mechanism. The one that have the alpha hydrogen, of course, is going to form the enolate. Are we getting it? The one that have the alpha hydrogen is going to form the enolate, which is going to form something like this. Let me just give the reaction mechanism. CH2, everyone knows this is minus, and then C double bond O, and then here is what? Hydrogen. Okay, everyone knows that. Now plus this other one, which is the acetaldehyde. So which do you think will attack which now? The enolate ion will attack this carbonyl group. So we have the enolate attacking this carbonyl group. Okay, so the product will be something like this. This. Are you getting it? And then you have C. Now if this attacks here, what do you think will happen to the double bond? it will kick up here. Okay, now this is going to now form, let me clean this. So I'm writing, I'm cleaning, because I don't wish to go to another slide to actually explain this. So what do you think will be the product now? The product will be very easy. This group here we attack here to now form CH2, right? C double bond O, and then what? H, and then here is what? Minus, and then here is what? H. Now what do you think can happen here? This one we abstract a proton from water, abi? Now if it abstracts a proton from water, it will now form the product. So when this one abstracts a proton from water, so that at the end of the day, what do you think will now be the final product of this reaction? It's very easy. The final product would be H, C double bond O, then CH2, C, here's what? OH, here's what? H, and here is what? Hydrogen, like this. Okay, and this will be the final product of this reaction. Okay, now this was what you have in your note. Now according to what we said, that as it is now, which of them is the alpha hydrogen? Now where do you think the elimination reaction will take place? Because we said that this one can be eliminated, water molecule can be eliminated from here. So you have here as what? H. We say it's alpha beta elimination. This is the what? Alpha carbon. This is the what? Beta. So we have alpha beta elimination. H lives here, OH lives here. So this gives us C double bond O, and what? Sorry, here becomes CH double bond CH, and then this will form this, and then this is what is called cinnamaldehyde. Okay, this is what is called what? Cinnamaldehyde, which is this product here to form cinnamaldehyde. Now if you look at your material, you agree with me that you have something like this. It's still the same thing with what you have there. So don't be, the way the structures are drawn here, they are drawn to confuse you. Don't be confused. As a chemist, if you draw this for anyone in the exam, nobody will fail you. Okay, nobody will fail you. Just understand the concept. So in your textbook you have something like this, your material, and then you have this one coming here, and then you have something like this, hydrogen. Then you have the double bond. It's still the same thing. Now let me show to you that it's still the same thing. Okay, this benzene ring is the same as the benzene ring here, right? Then after the benzene ring, what do you have here? You have CH, because here is CH that should be here. You have CH here, double bond. You have another CH here. Then carbon with oxygen here. Then finally what? Hydrogen. So they are the same thing. Okay, don't be confused by what you have in the material. If you write this, you are very, very correct. So this is what mixed aldol reaction is all about. So in a situation where I give you, let's say, react propanal and let's say ethanol. React propanal and ethanol. They are two different aldehydes, two different carbonyl compounds. Do you think they will undergo Aldol condensation reaction or mixed aldol? They are going to undergo this mixed aldol. Now you see that the process for mixed aldol reaction and the Aldol condensation reaction is actually the same, right? The process is the same, just some little variations. Okay, process is the same, just that the reagents that reacted are different. Okay, the last one is Cannizzaro reaction. Now the Cannizzaro reaction is a reaction whereby formaldehyde is the simplest aldehyde, which is this, right? I'm not going to show you the process or the reaction mechanism, but just note it. Whereby formaldehyde, when treated with sodium hydroxide, undergo a disproportionation reaction. So we are going to use two formaldehyde molecules here. It undergoes a deproportionation reaction. When we say deproportionation, it means that like 50% of the formaldehyde will be oxidized to form a carboxylic acid, and the other half are reduced to form an alcohol. Are you getting it now? So what do you think will be the product of this reaction? If we have two formaldehyde. So we have, let's say the first one. Let me write the first one. Now, when this is oxidized, what do you think it will form? When this is oxidized, it means you are adding hydrogen here. So it will form, oxygen there. So it will form AC double bond OH. Are you getting it now? Which is formic acid. Okay? Then this is for oxidation. So we put oxidation here. And then when it is reduced, when aldehyde are reduced, so we say reduction. When aldehyde are reduced, what is formed? An alcohol is formed. Okay? So this will form something like this. HCOH. And then you have H and what? H. Which can be written as 1, 2, 3. CH3OH. Right? And this also can also be written as HCOOH. Look at it now. HCOOH. So whenever this reaction occurs, this is proportionation reaction occur to form acid and then the methanol or an alcohol, you call it a Cannizzaro reaction. So what would be the product of this reaction now? HCOOH plus what? CH3OH. Okay? Now, the question is, in most cases, you will not always form formic acid. You will not always form what? Formic acid. Reason being that the, what is it called? The sodium hydroxide that is used for the reaction will react with this formic acid to form the ester, formic ester. To form what? The ester. So what will be the ester? The ester is in such a way that this hydrogen here combine with OH here to form what? H2O, water molecule. And then this group here will react, HCOO will react with Na to form this. So in most cases, the product is usually here will be Na plus the methanol. So this is for the Cannizzaro reaction. It does not undergo Aldol condensation reaction. So you may be asked, objective question, which among the following aldehyde will not undergo Aldol condensation reaction? Correct answer is what? Formaldehyde. Because why? It lacks an alpha hydrogen. Now, if you look at the structure of formaldehyde, this is H, this is what? C double bond O. Now, this is what? The carbonyl compound. Now, there's supposed to be an alpha carbon here, but there is none. So, it does not have an alpha hydrogen. Rather, the hydrogens are attached to the carbonyl carbons. Okay? So, that's for Cannizzaro reaction. And I believe that will be the end of this lecture on the Aldol condensation reaction. So, we've been able to discuss the Aldol condensation reaction, the compounds that undergo Aldol condensation, mixed Aldol reaction, and then we have the Cannizzaro reaction. Thank you very much for your time. Okay, thank you.